Hello, and welcome to the third part of our professional development series, Making Tinkering and Engineering in the Classroom. This is a presentation on engineering in the classroom. My name is Mary Reinhardt, and I'm from First Makerspace.
I'm Amber Hudson. I'm the Education Director at First Makerspace. We are excited to begin this third video in this three-part series, as Mary mentioned, on tinkering, making, and engineering. The focus for this one is going to be on engineering in the classroom. And we've been using NACCE's definition throughout this series. And NACCE defines engineering as using stuff to make stuff that does stuff. And I love the definitions that they have because it makes it really easy for kids to understand that all along they've been using how to tinker with different stuff, different materials, and they've then moved on to the progression of making stuff. And now we really begin to focus on the meat of STEM, which is the idea that the stuff that we've made does something. And so we're going to work through a process of defining what engineering looks like by using a sample project within a classroom. So as we look at engineering, we're looking at the branch of science and technology concerned with the designing of it, the building of it, the use of engines, machines, and structures. So when we say this is the meat of this whole idea of making, tinkering, and engineering, it really is the heart of it, because the employability skills that we've been preparing students for really come into play now as they start to think about the careers that might involve engineering. So we're going to focus on the engineering design process. I'm going to let Mary explain that now.
Wonderful. Thanks, Amber. And I want to echo what Amber said about engineering and technology really being the heart of STEM. That's where a lot of the hands-on learning happens. And of course, you see that with science and math as well. But there's so many ways to apply science and mathematics within engineering and technology. And so it is a process where students really build up to this. You can't just start an engineering project without any foundation. And so the engineering design process, which you see here, is really that series of steps that guide students through the engineering process as they solve problems. And this isn't limited to just student work. This is a process that real engineers use to develop new products and services. And we have an example from teachengineering.org here, which is a great website for lots of engineering lesson plans and resources. But there are all different types of engineering design processes. Some are cyclical, like you see, and they involve more of a loop. Some end with the improved process, which mimics more what happens in the real world, where a product actually goes to market and they stop iterating on the actual product. And so there's lots of different processes out there, but they all contain very similar steps. We're going to go through each step today and talk about what happens during that step and how you as the educator can guide students while they're working through the engineering design process and really facilitate teams that are functional and they get a lot of value out of the work that they're doing. One of the most important pieces of the engineering design process is the documentation of what happens when students and people are working together. And we call that an engineering design notebook. These notebooks, you can see a picture of an actual graph paper notebook on the screen, but they don't actually have to be a physical notebook. That's something that's really evolved as technology has evolved, especially in classrooms. Digital notebooks are also have become more popular. Whether it's digital or physical, engineering design notebooks contain sketches, notes, ideas, test results, to really document the design process, usually by one particular individual in the real world, but in the classroom, one could be used for a team project as well. They're really used as a portfolio where you can later go back as the educator and look to see how students worked through that process so that you can assess them based on their process rather than just their end product, which is a really important component of assessment with engineering. Sometimes the final design isn't necessarily the only thing that you're grading. You're also grading how they worked through the process. Did they document their steps? That is sometimes just as important as the final result. And you definitely want to give students credit for the hard work that they're doing with each other, the designs that they're doing, the testing that they're doing, even if their end product at the end of the unit wasn't always a functional prototype. And so this is a tool that you can use to help with assessment and documentation. In real engineering teams, you're going to see that this is also used to document intellectual property and to prove that a design was original to a specific engineer or inventor. They'll use these in patent filings to show that this was their design. In the classroom, we're not as much as concerned with intellectual property relating to the invention of products. Sometimes students invent wonderful products, but more so we're helping them learn how to do that. And so that's where it really comes in here. You can see that this physical one is bound together. Digital ones are usually, obviously, in either a Google slide format, PowerPoint format, even an Excel file has been used, so some type of spreadsheet. So lots of different formats that this can happen. The important thing is that it is happening and that students are documenting their work throughout the design process.
That's great, Mary. So as we jump into the steps of the engineering design process, in my own classroom, I'd have my students have their notebook open with them at all times. And with each of the steps, they were then placing information into that notebook so that they were documenting each and every step of the process as they went along. So as we jump into the steps of the engineering design process, we're going to break this apart with a definition of what the step involves, some details of what you might do during that step, and also share an example that I did from my own classroom walking through the steps of the engineering design process. So step number 1 is ask. And in this step, students are typically provided a question that is an overall arcing question over the project they're getting ready to work on. So they begin to immediately think about potential solutions to this problem that's been presented through the form of a question. So within their engineering notebook, they're writing down the word ask, and then they're also given some information that's going to help them determine what this project is going to look like. So for example, on the one on the screen that you're seeing, they're asked to identify a location on Mars where a colony can be built, and what the geographical and climate conditions might be like on Mars. In the project that I worked on in my classroom, we did this at the end of an animal adaptations unit, and students were introduced to Sandy the sandhill crane, and she's a migrating bird, a very large migrating bird. And in the process of her migration, it was time for her to lay some eggs, and she needed to provide a nest and a safe place for her babies. And so students were told that they needed to build a nest that was at least 40 centimeters tall. They were building out of index cards, masking tape. They had 50 index cards, 50 centimeters of tape, and it had to be at least 40 centimeters tall and hold a beanie baby bird from the top. So that's kind of the information that they were given after learning this story about Sandy. And then they started this brainstorming process. Okay, how am I going to build this? What materials do I have? All of those questions that come about by being given this prompt, they're recording those questions and the answers to those questions in their engineering notebook in this first step. In the second step, they're researching. So they know what the problem is. They know what the constraints are and the criteria for the project. They know what materials they have to use. So now they go off to do a bit of research. They're trying to figure out if someone has already solved this problem before. Is there information out there via the World Wide Web that would help them come up with a solution, a potential solution to this problem? So the research is done during this stage and then recorded in their engineering notebook so that they can go back and reference others who've already encountered this problem before and try to learn from what they've done. And then can they take what that person has already done and maybe improve upon it or change it to make it work in this situation? In step number 3, this is where they are imagining and planning. I think this is the fun stage of the engineering design process because they get to brainstorm any potential solution that might work. So for example, in this plan with Sandy, the sandhill crane, they're drawing out sketches. I would have students divide their notebook page into 4 different sections and try to come up with 4 different potential ideas for how to build Sandy's nest out of index cards. They're sketching those designs out. It's very quick, so there's not a lot of detail in this stage. They select a design. They're sharing those designs with the group that they're working with and then with the teacher before they can move on to the next phase of this engineering design process. In the planning phase, this is where they kind of take all of those things they've imagined and bring it into one final plan. So if students are working in a small group, they would each share their ideas with one another, show their sketches and their drawings, and then determine what would be the best plan for a positive outcome. And they might be taking part of one student's idea and another part of another student's idea and combining them together for that final plan. So there's a lot of collaboration that has to take place in this step to ensure that they're going to come up with a plan that they think will work. In the next step, this is the fun part where they actually get to create a design from the plan they've determined. So the students will build a prototype, and this obviously is going to take more time just because it's going to take time to build it. But this is where I would have students actually hand them the index cards and the tape and allow them the opportunity to try to create this tower they've been dreaming of from a two-dimensional picture that they've drawn in their engineering notebook to an actual physical model that's in front of them. There's a great opportunity here for students to take photos of what they've done, and that could also be included in their engineering design process because, as Mary mentioned earlier, we want to see the process. What are the steps that students are doing along the way to get them to that final plan? And this is where they may need to go back and make some changes because they may get a few parts of the tower built and decide that it isn't working right, or the cards and the way they were folding the index cards they thought might work, but it doesn't. And so they're constantly going back to ask those questions, reimagine their design, and improve upon their design. In the next step, this is where they get to test what they've built. So once they've created this prototype, they're trying to determine if their prototype is successful. This is a great place to collect some data and record that data in an engineering design notebook as well. This was where if students had built a tower, the actual Beanie Baby bird would come into play. I would sit that upon the top of the tower and time them to see if that nest could withstand the weight of the bird for up to 50 or 60 seconds, so about a minute. And at that point, that's where you see the excitement come on their faces as they successfully or not successfully build a tower that works. And if it doesn't, then that's a great time to send them back to again go try to improve upon their design and determine if they did meet the criteria, did they stay within the constraints of the project, and allow them a time of reflection. I think that's really important during this part of the process. Here are just a few example towers and students that were working on those with the Beanie Baby bird sitting on top of them. It was a fun project to do and an easy way to just showcase and introduce them to the steps of the engineering design process. The final step is to improve. This is where they redesign anything that needs to be improved. It's really important to not skip this step because students will often think, oh, I was successful, I did it, I met the criteria, mine is perfect. And I think it's important for them to understand that in the engineering world, there really isn't ever a perfect design. They're always going back to remodel it, to improve it, to make changes that are going to benefit maybe even the cost of the building or the cost of the project they're building upon. So students need to understand that just because they were successful doesn't mean they need to skip this step. And Mary, I'll turn over to you to share a few engineering projects.
All right, thanks, Amber. I want to echo what Amber said about improving as well. And if you find that with resources especially, so the products and actual things that they're using to create their design, if you're worried about the cost of those, that's one element where you may bring in the actual cost of different products in and approve their designs, give them a bank of how much different things cost. Maybe each index card is 10 cents. And this can be play money. It doesn't have to be real. But that way you might introduce an additional constraint in that way. Maybe they can only spend one virtual dollar on their nest that they're building, just to introduce that concept of limited resources when it comes to materials, because that's a real constraint that engineers face. And so that's just an idea that from our different work in classrooms that I wanted to share. There are so many different engineering projects that you can do. This is a really great way to infuse STEM into your classroom, no matter what grade level you teach. And it directly aligns to the standards as well. Every science standards has a component of engineering standards at the bottom. And so here are some examples that we have. Our TeacherGeek kits are they're all great engineering projects. I listed Build a Boat, but there are several: Toy Design Workshop, Projectile Launcher, like we'll show here shortly. Some other ideas: straw rockets are also really fun, a great activity to get outside as well. Bridge design is a classic engineering project, and you may have done that in different ways. And that's one of those projects where you can continue to have it evolve as well. You may start a project in first or second grade where they're using straws or popsicle sticks, and then it evolves to using balsa wood as they get into middle school. And just additional, maybe they are developing larger bridges in high school. And so lots of ways for these same topics to evolve over the course of several grade levels as well. Rube Goldberg type crazy contraptions can be done in several ways as well, with several different varieties of constraints. Lego Mindstorm kits are fantastic for not only that designing and building, but also they have a programming component as well. Lots of ways to infuse computer science in these too. Marble runs can be done at several grade levels. Egg drop is another popular one, an old science fair classic. And so you can see these are several examples of simple engineering projects that you can do without a lot of extra kits or resources, and that can be done and applied to several different settings. As we take a look at why engineering, it's another element to add, another different project to do. One thing I want to share here is that it is aligned to the academic standards in Indiana. It's part of the science standards at several different grades, all the way up through 6th grade, and then it branches off into its own domain of standards. But in addition to meeting those academic standards, students are also developing really solid employability skills. And this is where the real value of working through these STEM and engineering projects comes in. Students have to work in a team. They have to collaborate. And there's nothing quite like that sense of pride that students have when they have a finished product. When you make something, that sense of pride is such an important component. And that's why it's also a great way you can infuse that into parent communication by allowing students to take home their objects if it's made with something consumable, or even a picture sent home is a great way to share that with parents and other community members, and give students a really great way to showcase their work. Students also work through data collection. That's a great way to infuse math and engineering together. And of course, perseverance, critical thinking. These are all important employability skills that students develop by using the engineering design process.
We wanted to share with you an actual project. As Mary mentioned earlier, TeacherGeek is a small company that creates some amazing STEM kits, and the projectile launcher I happen to have here is a fantastic engineering design project that launches a ping pong ball into the air. And once you have the projectile launcher built, there are a number of labs that can follow up the actual building process. So you're getting your science, your technology, your engineering, and math are all coming into play in this particular process as they walk through the steps of the engineering design process and the designing of their launcher, the redesigning of their launcher, improving what it can do, and then testing it to see if it works properly. So enjoy this video as we time lapse you showing a quick projectile launcher build. Our next project of the week is the TeacherGeek Projectile Launcher. You can find the information needed for the build guide and the directions at www.teachergeek.com. Once you have the TeacherGeek build guide for the projectile launcher, it will tell you exactly what TeacherGeek materials to collect and gather to be able to build a successful projectile launcher. Once you have your pieces collected, you'll also want to gather some simple tools. These are the TeacherGeek provided tools. The items you will need for this build are the screwdriver and some wire cutters. to find the directions for the projectile launcher, you'll want to visit the TeacherGeek website. That website is teachergeek.com. What I love most about this website is that it has great detail and resources for teachers. Each build that TeacherGeek has a card on their home screen. I'm going to find the one for the projectile launcher, which is right here. If I click on this, what it will lead me to are all of the directions I need. So if I wanted to order more of the projectile launcher, I could do that through here. What you're also going to find is the age range. This particular build is really geared for 8 to 12-year-olds. Here's a video. If I wanted to see the projectile launcher built, I could watch that video. And then this is the really important part for teachers. The Go Guide is your set of directions. You can print that in a PDF form or a Word document form. Next to the Go Guide, you're going to see the optional labs. As an educator, I would want to carry this further within my classroom. Here, we've built the projectile launcher. Now what do we do with it? There are 3 labs available: the Precision and Accuracy Lab, the Hit the Target Lab, and the Projectile Motion Lab. Those documents can all be found there for printing. Then there are optional challenges, what they call the Bullseye Challenge, and the Engineering Notebook pages. The Engineering Notebook process is vitally important when you're doing an activity like the projectile launcher. And so there is a simple and a full version of the Engineering Notebook page there, as well as additional resources, extra protractors. Every TeacherGeek activity has a STEAM Market Challenge where students would advertise for their product they've created, and then an additional link to those same engineering design challenge notebook pages. So amazing resources here. It'll tell you what tools you need, and it'll tell you what materials you need to be able to build that. And then you'll also find the NGSS standards at the bottom of the page. So great resource for teachers. Always, if you're doing any kind of TeacherGeek build, go to their website and find all the materials that you need at teachergeek.com. Following the build guide directions, you're now ready to start this projectile launcher build. You're going to begin with the whole plate and begin by screwing different pieces in to create the lever that will project the ping pong ball into the air. In the next set of directions, you're going to attach a few more pieces that will control the power and the force that the lever has when launching your ping pong ball. Once your dowel rod is in place, you can use the protractor and the inclinometer to adjust the angle at which your projectile launcher launches. The final set of directions will tell you all the details about how to attach those to your projectile launcher. You can add your own personal touches to the final pieces of your projectile launcher, and you're now ready to test its strength and its accuracy. Here are 2 examples of ping pong ball launcher challenges that you can complete when your build is done. The first one is an accuracy challenge where you're trying to hit the bullseye. The second one is a siege challenge where you're trying to knock down as many cups as possible. There are several TeacherGeek resources out there once your projectile launcher has been built. On the PowerPoint and the resources that you have available to you, you'll find the launcher build guide, which are the step-by-step directions for building the projectile launcher. And then once that projectile launcher is built, you have access to a number of labs that will allow students the opportunity to test how well their projectile launcher works. So the precision and accuracy lab, the hit the target lab, and the projectile motion lab. And of course, that's really where you see the student engagement come in when they have an opportunity to test and see if their projectile launcher is successful. We appreciate you taking the time to listen and watch our video on engineering in the classroom. This is the end of our three-part series, and we would love to help direct you in products that are out there or help that you need within the classroom. You can visit our website at firstmakerspace.com, and you'll also find all of the additional resources at keepindianalearning.org. Thank you for your time today.